Bienvenue à tous. Je m'appelle Peter Jackson de l'Université du Nord de la Colombie-Britannique. Je préside la séance plénière d'aujourd'hui. Merci à tous d'être venus. Welcome, everyone. I'm Peter Jackson from the University of Northern British Columbia. I'm chair of today's plenary session. Thank you all for attending. Well, today is the last day of Congress, so it's an exciting day, and I hope you look forward to it, as do I. I would like to start by acknowledging the indigenous peoples of all the lands that we are on today. From coast to coast to coast, we acknowledge the ancestral and unceded territory of all the Inuit, Métis, and First Nations people that call this land home. La présentation de ce matin est intitulée Exploiter la croissance explosive et l'intelligence artificielle pour faire face aux événements extrêmes dans un climat en changement. Il sera présenté par le Dr. Matthew David Hall de NVIDIA. This morning's presentation is titled Tapping into the Explosive Growth in Artificial Intelligence to Tackle Extreme Events in a Changing Climate. It'll be delivered by Dr. David Matthew Hall of NVIDIA. Dr. Hall is a senior solution architect and data scientist at NVIDIA, where he specializes in AI applications for weather and climate. Prior to joining NVIDIA, he was a computational climate scientist at NCAR and at the University of Colorado Boulder. Throughout his career, he has made significant contributions to the fields of computational physics, climate model development, and artificial intelligence, including co-authoring the non-hydrostatic atmospheric dynamical core on the Energy Exascale Earth System Model, E3SM, and the High Order Methods Modeling Environment, HOMME, non-hydrostatic atmospheric model for the Community Earth System Model, CESM. Dr. Hall has, the talk will be roughly 30 minutes long, and we'll have lots of time for questions at the end. Dr. Hall has been suffering from bronchitis, so we have his presentation recorded, but he is attending and will be able to answer questions live at the end as long as his voice holds out. Please type your questions in the Q&A box. If you could indicate your name in the question, that would be most appreciated. So with that, I think we will start streaming Dr. Hall's presentation. I'll just stop sharing my screen.
Hello. Thank you for inviting me to speak with you today at the 58th Congress of the Canadian Meteorological and Oceanographic Society. For those of you who don't know me, I'm a senior solution architect who spent the last 7 years focusing on AI for weather and climate at NVIDIA. Prior to that, I spent about a decade developing atmospheric dynamical cores for climate models, like NSF's CESM model and the Department of Energy's E3SM model. I also hold a joint position as adjunct professor at the University of Colorado at Boulder. I emphasize the last as much of what I have to say reflects my own viewpoint as a researcher and does not necessarily reflect the position of NVIDIA as a company. All opinions are my own. Let's start by taking a look at the big picture. AI weather forecasting is a relatively new approach to weather prediction, offering new tools with some undeniable advantages over conventional numerical weather prediction solvers. AI forecasts have demonstrated accurate medium-range global forecasts at 25-kilometer resolution, using a tiny fraction of the time, energy, and compute of conventional PDE solvers. AI weather models trained on datasets like ERA5 match the accuracy of IFS, but at 10,000 times the speed while using only about 1/10,000th the power. One advantage of this is the ability to generate enormous ensembles with 10,000 or more members in an embarrassingly parallel fashion. Huge ensembles have the potential to capture rare but extreme weather events, tropical storm tracks, and reduce forecast uncertainty overall. Another major advantage is the speed with which such a model can be improved upon. A new AI model can be trained from scratch in a matter of days on a sizable GPU cluster, so they can evolve quickly and improve at a rate that handwritten software just can't match. AI models of this sort are natively optimized for GPU-accelerated computing without the need to port or refactor their code to take advantage of massive parallelism. Once trained, they are small and lightweight enough to run on a single workstation rather than a supercomputer. The enormous speed and energy efficiencies of AI models have the potential to transform how weather prediction is done. What probably matters most in the end, however, is, are these AI models useful? ECMWF has been field testing many of these models, including ForecastNet, Fuji, GraphCast, and Pangu Weather, and has found them to be skillful. In response to these developments, ECMWF began developing their own medium-range weather forecasting model called AIFS. On June 3rd, ECMWF posted a paper to arXiv that summarizes their recent work on AIFS. They conclude that AIFS produces highly skilled forecasts for upper air variables, surface weather parameters, and tropical cyclone tracks, amounting to a forecast advantage of more than 12 hours for longer lead times. It is apparent that AIFS represents a step change in forecast skill compared to IFS, they quote in the paper. The plot shown here represents the anomaly correlation coefficient of geopotential height predictions at an elevation of 500 hectopascals. Higher is better on this plot. The red line shows the quality of the IFS model evolving over time since 2004. The black line shows the quality of the ERA5 reanalysis dataset used to train their AI model, and the blue line shows the clearly superior accuracy of their new AIFS model. It's not all roses, of course. Present-day incarnations of AI models also have a number of shortcomings. Some common criticisms include regressive AI models optimized for multi-day prediction tend to predict fuzzy states that are more similar to the ensemble mean rather than a sharp ensemble member. They only operate at 25-kilometer resolutions, which is much coarser than the best 8 to 10-kilometer operational models. They are still dependent upon traditional data assimilation methods for their initial conditions. They inherit the limitations of the model data they're trained upon, such as the limited precipitation skill in ERA5. As we'll see, each of these issues appears to be a short-term bump in the road, with solutions already beginning to quickly emerge. Beyond their short-term limitations, many open questions remain. For example, how well do AI models respect the known laws of physics? To what degree can they generalize to new unseen physical scenarios? Can they generate accurate forecast ensembles? How do they manage to take such large time steps? And how do they make predictions using incomplete information? Can we trust them when we can't decipher their underlying mechanics? Will AI models continue their rapid advance, or will they simply plateau? What is the future of conventional numerical weather prediction development programs in a world with AI models? I am not claiming to have all these answers. AI forecasting is still very new, and the answers are likely to evolve over time as we learn to work with these new tools. I will, however, review what's possible today and try to guess at where it's headed tomorrow by extracting hints from the larger AI industrial revolution. Let's zoom out a bit and look at the bigger picture for a moment. Some people are enthusiastic about AI advances in numerical weather prediction and see opportunity. Others are skeptical or downright unhappy about it. I think to better understand where things are going, we need to take a look at the larger context. The changes happening in numerical weather prediction are far from unique. AI weather forecasting represents only one small facet of a much larger AI industrial revolution. An ever-widening set of professions are experiencing disruption due to AI, and as compute power continues to grow, artificial intelligence will likely continue to improve rapidly. AI is poised to transform most every industry over the next decade. Zooming out even farther, we see the AI revolution is just the latest stage of an ever-accelerating technological feedback loop. Farming freed us up to do other things. Writing let us store and transmit information. Fossil fuels enabled us to power large machines. Each advance provides a competitive advantage and enables further advances. From the timeline shown here, it's clear that the interval between advances has been shrinking from thousands of years to decades or less. When ChatGPT emerged in fall of 2023, you could expect roughly one major AI advance per month. Now we get significant news on a weekly basis. If this pattern continues, the amount of change we will see in the next few years could be staggering. When we talk about artificial intelligence, we're usually talking about deep learning. Over time, other techniques may also rise to prominence, but the fundamental ideas remain. Machine learning techniques like deep learning leverage vast quantities of compute power and convert it directly into extraordinarily sophisticated pieces of software. The present-day incarnation of artificial intelligence is driven by the power of deep learning, which is a simple but very powerful optimization technique that can build software of nearly unlimited complexity, far beyond the practical limits of what people can code by hand. Using the simplest possible optimization technique, gradient descent, in a very high-dimensional space, it employs enormous amounts of compute to sculpt the software to our specifications. With enough compute and enough high-quality data specifying your desired outcome, you can build almost anything this way. Deep learning converts data and compute into software. The more compute you have, the more sophisticated the solution it can produce. In the early 90s, deep learning couldn't accomplish very much at all due to insufficient compute and data. I gave a talk as an undergraduate in the early 90s on deep learning, but although most of the pieces were there, it didn't amount to much for another 20 years. Compute has increased by roughly 10 million times since then, turning deep learning into an immensely powerful tool. As a result, models have grown increasingly sophisticated over time, from simple MNIST digit classifiers up to ChatGPT models, which can perform a wide variety of tasks, and it may soon achieve human-level reasoning. AlexNet was the first turning point where deep learning proved its value. Powered by NVIDIA GPUs, that model won the ImageNet image classification competition in 2012, to nearly everyone's surprise. After that, deep learning grew pretty fast. 6 years later, the largest models were several hundred times as large. But the 2018 invention of the transformer by researchers at Google changed the game again. Since that time, the largest AI models increased their compute demand by 100,000 times. This is because the transformer is both remarkably flexible and capable, but also massively scalable, enabling models of enormous size and complexity. The plot shows the compute requirements needed to train important models as a function of time. Note, the vertical axis is logarithmic. The blue line shows that the models grew by about 2 orders of magnitude in just 6 years. However, after the invention of the transformer, model growth has been explosive, gaining an additional 5 orders of magnitude in the subsequent 6 years. NVIDIA has been working continuously to meet the increasing AI demand ever since that first AlexNet moment. We have been producing faster and more energy-efficient systems for decades. This particular slide was taken from a talk by our chief scientist, Bill Daly, where he discussed how we've been able to accomplish this. Gains in AI performance come from improved representations of numbers within the GPU, instruction sets with ever more complex instructions that amortize the overhead of retrieval and storage across many operations, smaller chip fabrication size, and improved use of sparsity, in that order. Our latest chip is called Blackwell, and we have 2 generations of chips nearly completed beyond that. Bill is confident that he sees a clear path forward for at least 3 more generations. NVIDIA's latest hardware offering is the Grace Blackwell 200 NVL72, which is a remarkable machine. It has 72 tightly coupled Blackwell GPUs that act as a single unit of compute, with 720 petaflops of AI training and 1.4 exaflops of inference performance in a single rack. It's basically a massively parallel, fully integrated exascale machine in a box the size of a person. The compute and power efficiency gains of these systems continue unabated. In order to train a giant 1.8 trillion parameter mixture of experts model, it took 8,000 Hopper GPUs about 90 days. You can train the same giant model using just 2,000 Blackwell NVL72s, using just a quarter of the power. NVIDIA has had great success applying our three superpowers of accelerated computing, artificial intelligence, and high-end computer graphics to a wide variety of important issues, including biological research, autonomous driving, healthcare, and robotics, amongst others. But one of the most important initiatives at NVIDIA is called Earth 2. In November 2021, our CEO, Jensen Huang, introduced the Earth 2 Digital Twin program to develop technologies for improving the prediction of Earth's climate and weather, based on advances in high-performance computing and artificial intelligence. At NVIDIA, we build digital twins of many systems to help predict their behavior ahead of time. His ambitious vision was to build a similarly accurate digital twin of the Earth that would allow us to rapidly and interactively explore and visualize how our choices impact Earth's weather and climate across a wide range of temporal and spatial scales. We're working to make the Earth 2 vision a reality by leveraging the three miracles of accelerated compute, artificial intelligence, and visualization in the form of omniverse digital twins. The accelerated compute enables researchers to generate large quantities of high-quality data, which can then be used to train extremely fast and accurate AI surrogate models. These models and their output can then be explored interactively in realistic 3D ray-traced environments from nearly any device, using our Omniverse Cloud platform. The speed and interactivity of this approach has the potential to build a qualitatively different type of model than the traditional climate models and weather models we are all familiar with. NVIDIA is a company that builds platforms and systems that enable researchers to do things they could not do in any other way. Our goal with Earth 2 is not to build a full digital twin of the Earth on our own, but to provide amazing tools and resources for industrial and academic partners to utilize. In addition to our fundamental technologies, we have recently released our Earth 2 Studio, which is designed to help researchers get started working with AI models of weather and climate as simply and easily as possible. We also have our Earth 2 Inference service, which is in early access. Its goal is to make those same models easily accessible from the NVIDIA cloud, so powerful AI model predictions are just an API call away. In a related development, NVIDIA has begun offering NIMs. What's a NIM, you say? An NVIDIA Inference microservice. It's a pre-trained AI model in a container with everything needed to run it and host it, including the Triton Inference Server and TensorRT, as well as all important libraries, all optimized for your specific GPU. You can access them in the cloud or host them on your own machine. AI for climate and weather is developing more quickly than ever. So let's sample some of the recent important advances and research projects ongoing both inside NVIDIA and from the larger research community. There are many exciting research frontiers that the Earth 2 team is pursuing simultaneously, including accelerated versions of kilometer-scale global cloud resolving models, weather-climate foundation models, AI data assimilation techniques, AI downscaling techniques, and more. NVIDIA's ForecastNet was our first foray into AI weather modeling. We began with weather as it's simpler, had a great deal of high-quality data available, and the prediction of weather extremes is one of our top priorities. ForecastNet was first released to archive on February 22, 2021, just a few days after Ryan Keisler's paper entitled Forecasting Global Weather with Graph Neural Networks. Together, these two papers demonstrated that practical and realistic AI models of medium-range global weather forecasting were achievable. The ForecastNet paper, in particular, trained a large model at the full 25-kilometer resolution provided by ERA5 reanalysis data, demonstrating that operational-scale AI weather models are possible. Active research continues on ForecastNet at NVIDIA. We've improved its stability to long rollouts and are working toward higher resolutions, and an understanding of how best to produce and take advantage of enormous forecast ensembles. There are many high-quality AI forecast models, and comparing their strengths and weaknesses in an objective way is challenging. As part of our Earth 2 model intercomparison project, we have recently submitted a preprint to archive discussing how lagged ensembles can be an effective tool for standardizing the comparison of probabilistic weather models. We are also pursuing new ideas in the space of AI-assisted data assimilation. Using a denoising diffusion model, we generate plausible atmospheric predictions and iteratively refine them until the predictions match our sparse observations. Here are some very early results from this model. You can see that from just a handful of observations, the technique can generate reasonable predictions for wind speed and precipitation. AI weather forecasting is highly valuable, but weather alone was never our final goal. We're also looking to build coupled AI models of both weather and climate. At GTC 24, our collaborator, Dale Duran and team from the University of Washington demonstrated exciting steps toward a fully data-driven climate model. He showed that his coupled deep learning models of atmosphere and ocean were able to very accurately represent today's climate, with an autoregressive simulation that remains stable over 100-year rollouts taking 6 hourly time steps. PDE solvers integrating the physical laws of motion remain the most accurate way to generate likely future climate scenarios, as we have no observations of similar states to train an AI model upon. By pushing to very high resolutions, we can enter the cloud resolving regime, where important phenomena can be explicitly resolved using the laws of physics, rather than ad hoc subgrid scale parameterizations. This should make for a much more accurate model, as physical parameterizations are the largest source of uncertainty in such models. Simulations at these resolutions merge weather and climate, enabling statistical predictions of extreme weather for every region. Simulating kilometer-scale global climate is a grand challenge due to its immense computational and storage requirements. AI surrogate models, once trained on this data, can make these simulations far more practical to run and interact with. But first, we need the training data. NVIDIA is working together with the Weather Company and the Max Planck Institute on generating custom kilometer-scale training datasets. The Accelerated Computing Wing of our Earth-2 program has been working closely with the Max Planck Institute and others to accelerate the ICON 2.5 kilometer simulation to at least 20 times the CPU throughput speed in order to generate sufficient data for AI model emulation. At our recent GTC 24 conference, we announced our CoreDiff model, which is a generative diffusion model that downscales 25 kilometer Era 5 data to 2 kilometer radar assimilated WRF data over Taiwan. AI downscaling is another approach we are pursuing to help generate the local, very high resolution predictions required by many downstream applications. The CoreDiff model over Taiwan was a proof of concept. Since then, we have been exploring the possibility of customized CoreDiff-like models for different regions of the globe, as well as the stretch goal of a global CoreDiff AI downscaling model. We have been working to assist researchers to expand their efforts to build large foundation models. Foundation models are enormous but expensive pre-trained models that are highly capable due to their generality. They provide a foundation upon which specialized models can be built for various downstream applications through model fine-tuning. Foundation models, like those provided by the NASA Impact collaboration with IBM, will provide enormous, skillful open science models for the science community to share and build upon. One of the major criticisms or challenges of AI forecasting is that their predictions often appear to be fuzzy compared to conventional numerical weather prediction forecasts. This is because of the chaotic nature of the problem. When predicting a single state from a distribution of multiple possible outcomes, the best you can do is predict the ensemble mean. Generative models, like diffusion models and GANs, however, are able to capture the entire distribution of possible states, overcoming this limitation. Google's GenCast model decisively demonstrates that AI model forecasts can retain sharp features needed for quantifying and detecting extremes. GenCast v2 uses a diffusion model to predict an ensemble of stochastic 15-day global forecasts at 12-hour time steps and 25-kilometer resolution for 80 variables in just 8 minutes. They claim it has greater skill than the best conventional ensemble weather forecast model, namely ECMWF's ENS model, on 97.4% of the 1,320 targets evaluated, and that it better predicts extreme weather, tropical cyclones, and wind power production. Another major criticism of AI weather forecasting is that, despite its forecasting speed, it's still dependent upon conventional numerical weather prediction models for data assimilation to generate its initial conditions. The recent publication of aardvark weather by a large team of collaborators from many institutions demonstrates that the end-to-end medium-range global AI forecasting is feasible. An extract from their abstract reads, "We present aardvark weather, the first end-to-end data-driven forecasting system which takes raw observations as input and provides both global and local forecasts. Local forecasts are produced for temperature, mean sea level pressure, and wind speed at geographically diverse set of weather stations, and are skillful with respect to IFS HRES interpolation baseline and multiple lead times." I think you can probably tell by now that I think AI is going to be a really big deal. But let's ask this rhetorical question anyway. Will AI dominate the future of weather prediction? I can't see the future, but I believe that it will. It has many advantages. It's fast, power efficient, and grows more powerful with compute. New models can be trained in days, and it can learn directly from observations. The limitations and criticisms of the first waves of models are falling like dominoes as the second wave of models emerges. These models are not hype, and they are not going away. So it's best that we embrace them as a valuable additional tool in our toolset and learn to use them well. As for the larger AI revolution, I recommend we all buckle up because it has only just begun.
Great. Thanks very much.
Hi, everybody.
Hi, David. Very interesting presentation. I think will generate lots of questions and discussion. David, I'm not sure if you can read were you able to get into the chat? You can read the questions as well?
I can, yeah. I see 4 questions in the chat.
Yep.
Do I
Okay.
go through them?
Yeah, why don't we do that? And why don't you start so they can get voted up and down. So that's why they'll change positions, and then maybe more added as well as you go along. So maybe you could start by reading them out or would you like me to read them out for you and save your voice for answering? What?
No, my voice isn't that bad right now. I'm doing pretty good. So
Okay.
I
Well,
can go ahead and read them and then attempt to answer them.
Sounds great. Thanks, David.
Okay.
Go ahead.
So the first one says, when you run an ensemble with thousands of members, how do you isolate extreme events that are likely to occur? I would imagine most runs with that many members would include some number of extreme events. That's an interesting guess. So we did some experiments where we looked back at historical events like a heat wave. There's a video link I can post if I was fast enough. But basically, these extreme heat waves are not detectable by normal ensemble members, like 40 ensemble members that you get from like IFS runs or sub-seasonal to seasonal runs that exist right now. If you pump the number of ensemble members up to 1,000 or 10,000, it really covers the PDF of all possibilities really well. And you will get some fraction of them that show this extreme heat wave if it is a possibility. So in this case, it shows that there's like 5% chance or 10% chance of these really extreme heat waves happening, which doesn't sound like that much, but they're very dangerous events. So if a 5 or 10% chance pops up, that means you should take it seriously. If there's no extreme heat wave possible, you're not going to get an extreme event. I mean, you may get 1 out of 1,000. That means there's a 1 in 1,000 chance of it occurring. So you don't get stray events that are non-physical unless your model is wrong or your initial conditions are wrong, or you're just really unlucky with like the chaos, but I think very rarely. So these things are real. And yeah, more ensemble members means more chance to predict them and more chance to prepare for them. So that's what I would say to that one. Okay, we have a new upvoted one. David, thanks. Can you speak more about extension of climate, where values could fall far outside training data and forcing is time evolving? Yeah, it's challenging, of course. That's why we started with weather, because it's so much easier. With weather, you can observe like the actual state of the Earth. You can train a model purely from observations. We see what it's doing and can predict what it's doing and check if we're predicting it correctly. With the future, it's harder to see, you know. So PDE solvers, these really sophisticated climate models, are still the only way currently to generate data. So we have to generate a lot of data on different scenarios under different conditions to train a sufficiently skillful AI model that does the same thing. You don't have to just randomly simulate things, though. I mean, there's something we're not doing yet, which is targeted data training. So the AI model is really good at this, but it doesn't know what to do under this scenario, or if we have this much heating. There are weak spots in the training data, and you can identify those and then run your PDE solver to fill in those weak spots. So yeah, I mean, eventually it may be possible to emulate each of the components separately, the ocean, the atmosphere, exercising them all in these similar ways where you perturb them in all kinds of crazy ways to get all their behavior. And then you couple them together and basically have an AI emulated version of a climate model, which can do the same things. So it's possible that we may be able to eventually find this other approach as well, but I'm not 100% sure yet. All right, let's see. The next question is about ethics, which is way outside my pay grade. What is the intersection of, it got moved. What is the intersection of AI ethics and AI-enabled numerical weather prediction? We know there's considerable potential for racial bias across all AI applications when the same occur in numerical weather prediction. Examples, poor areas are often data poor areas are often attractive for energy and water demanding data centers needed to train models. Yeah, of course, AI inherits all the ethical biases and mistakes that we have in general. So they're trained on data-rich areas. They'll have more information on data-rich areas. And yes, definitely, cooling centers are more likely to be in poor places where people are not able to object to them. AI does not change our fundamental underlying ethics. That's up to us to do. It's just a tool. It's a very powerful way to produce software. We can produce software manually, or we can produce software by AI that's much more powerful, but that does not solve any of society's problems. And in some cases, will exacerbate them because it's going to draw even more energy and amazing, there's going to be amazing changes. Yeah, so I'm not going to claim AI solves ethics. It sure doesn't. All right, let's see. The GPUs required for training any useful model seems to be only within reach of groups owning supercomputers like you. Well, I don't know, but yes. Leaving others in the dust, so to speak. How can university researchers best help this revolution under such circumstances? It is a challenge, of course, which is why so much research in AI has been moving to industry, because you really do need extremely large compute to build the most cutting edge models. And that's just increasing over time. In the next couple of years, they're going to be building like a megawatt and then 10 megawatt data centers, which are like the size of states. And yeah, so I mean, only a few people can do that. However, that doesn't mean academic research is completely left out in the dust. You can build these foundation models like NASA is doing, and then release them as an open science tool. And the foundation model was very expensive to train, but it's not that expensive to fine tune or build on top of. So for example, they built HLS foundation model for observations, and then you're able to fine tune it for detecting floods and wildfires and crops. And those fine tunings are not particularly expensive because they're just taking the existing model and adding a little bit more data on top to make it more skillful in one particular area. So fine tuning is one of the places where you can build a new and skillful model. And I mean, I can't go over all the different possible ways that academics can contribute because, you know, it comes down to extreme cleverness. But yeah, the biggest models will be few and far between. Hopefully some of them will be open source and shared, and some of them won't be. All right, what's next? Can AI models replace conventional numerical weather prediction since they run 10,000 times faster? Don't they actually depend on conventional NWP? So yeah, AI models right now perform similarly to NWP. They can be more accurate in some ways. The resolution is not as high. They are much faster and more power efficient. So there's some trade-offs right now. They're mostly fuzzier because they do the ensemble mean thing. Once we get all these pieces in place where data assimilation is coming directly from observations and diffusion models are used instead of regressive models so that it actually creates sharp predictions, you won't actually need the Era 5 data set anymore, although you will still probably use it for pre-training because it's there, it's available, and it's a good place to start. So yeah, hypothetically, they probably can replace numerical weather prediction I know a lot of people don't want to hear that. There may be places where NWP changes its role instead, which is that, like I said, if you're missing data or observational data or data where you're poorly instrumented, you can run numerical weather simulations to shore up that data, just like I was saying with the climate thing. So I think NWP may just change how it's used, but I can't really be certain. So yeah, my money would be on AI NWP in the long run, but we'll wait and see, I guess. All right, let's see. These things keep moving around. Let's see if I can find which ones I haven't answered. How does the dazzling development of AI coexist with our efforts to reduce energy consumption, which is a major cause of climate change? As computers become more powerful, they also consume more and more energy, don't they? Well, there's my opinion, and then there's NVIDIA's opinion. So NVIDIA's position is that, yes, of course, more compute means more energy, but NVIDIA's systems, each of them, if you notice, is like 20 times as power efficient as the previous one. So if you were to keep your compute load fixed, every time we release a new generation, Hopper, Blackwell, Rubin, and whatever's after that, you will see like a 20 times drop in your energy utilization and the footprint of your data center, because you don't need as many computers to do the same. So less water, less power. If you fix your compute, it just gets better over time. Unfortunately, that's not what people do. The more compute you give them, the more compute they use. And it just gets more and more valuable. So obviously, it's up to us as a society, to regulate how much power is used for what. Right now, it's only like 1 or 2% of the total global consumption goes to these things. But it's going to become such a large part of society, in my opinion, in the next few years, that the energy will be a bottleneck for AI, and it will be a significant issue of how much energy we want to spend. But yeah, it's an issue. NVIDIA is doing the best that we can with it, but the value seems to outweigh the energy savings. So it just keeps going up. In the grand scheme of things, we don't have that much great weather data. We get new weather at the rate of once per day. How can we prevent overfitting as AI NWP models reach billions or tens of billions of parameters? Well, first, they don't need tens of billions of parameters. ForecastNet, for example, is about 200 million parameters, which is a tiny, tiny fraction of what ChatGPT-4 is. It's like a trillion or several trillion. So you don't have to make the model infinitely large. Once it captures all the physics, just like your weather model doesn't need to grow infinitely large over time, right? Once you get the physics, if you get it all right within your resolution limits, it doesn't have to get bigger. More data makes it more accurate because you fill in the errors and you reduce the uncertainties. And there is actually a lot of weather data, historically speaking, and from observational stations that has not been utilized because they have different resolutions in space and time. And so there's still a lot of data to squeeze out a lot more quality. And yeah, of course, we only get new data for 1 day per day. But once you get the physics down, it should be able to predict the future just as well as any handwritten piece of software, and probably a heck of a lot better because you're not making all these assumptions. It can find patterns that humans just can't guess. Sorry for the cough, guys. That's why I'm recording things. In AI models, we already did that one. How can you run an ensemble with 1,000 members? We did that one. They keep moving. Great presentation. I'm wondering how AI models will perform in the Arctic, where there's a notable lack of observations. So I wonder if AI models will have issues in that part of the world. Looking to see if you have any comments on this. So it doesn't have to have data. So if you think of it just as a simple curve fitting exercise, you're like, well, no data in the Arctic, no good in the Arctic. It's not quite that simple, because the deeper and the larger these models get, they learn to write basically software subroutines. There are multiple levels calling multiple functions that do multiple things. And just like any other piece of software, if you capture the underlying physics, you're going to have similar physics in the Arctic that you're going to have somewhere else. Like the atmosphere behaves the same way, you have hydrostatic balance, geopotential, geostrophic balance, all these things. And so the goal is to exercise the model to the point where it learns the physics. And you have to test for that. You don't know. When the model is first trained, maybe it overfits. Maybe if you let it train much longer, there's something that happens called grokking, where the model moves away from the overfit solution to like the least, like basically the Occam's razor solution, like the best possible solution for that problem. You don't know when this happens. You have to continuously validate and measure how well it's capturing various phenomena, how well it's capturing physical, the underlying physics by doing perturbation experiments, everything you would do to test any new weather model. But it should be made fast and like repeatable, because you're going to have a new weather model basically every time you update or retrain an AI model. And so we need to learn to get good at this. Where okay, let's see. Which ones am I missing? They keep moving so much, I don't know which ones I haven't seen yet. Have we yet devised a way to understand and communicate uncertainty in AI models? Okay, so there's all kinds of different sources of uncertainty. So this is a difficult question to ask. You've got initial conditions uncertainty, model uncertainty. You've got the uncertainty in your measurements. You've got the uncertainty in the predictions. Like you can produce an ensemble, but you don't know if it's the right ensemble. There's all kinds of ways there's uncertainty. So it's hard to answer that. But so if you, just like with a traditional model, you can perturb the initial conditions and you'll get different ensemble members. You can perturb the model and you'll get different ensemble members. You can do this for like known data that's been produced by the IFS. For example, they've done 40 ensemble members over a long period of time. And we can see if the AI model is predicting similar ensemble predictions to those models. And I mean, I don't really know how to get down to more than that on this question, because there's just so many different ways to take it. So if you have a more detailed question, please feel free to post it and I'll attempt to follow up. What is the role of physical understanding in a world of surrender to AI modeling? Well, it would be nice if we understood what the AI models are doing. I think everybody agrees on that. And Anthropic is working really, really hard on this. Some other people are too, but they seem to be the ones making the most advances. They're focusing on large language models because they want to know why Claude 3 does what it does. And they've actually produced a paper recently on mechanistic interpretability that has made some really good strides. So they can see when the model is doing what to some degree. And I think it's the first big step forward I've seen in this area. So if we can extract what they've learned and apply it to these smaller, simpler models, we may soon be able to learn which group of neurons represents conservation of math, if any. Which group of neurons, represents certain phenomena in the atmosphere. We submit a phenomenon and then we see which neurons light up, and then they have this way of doing a what was it called? Anyway, they train another AI model to identify which neurons do what. So there's a chance that we will get to the point where we can actually reverse engineer these AI models to see what it is they learned and how they work. Because right now what we have is a compiled binary, effectively. I mean, it's not exactly, but that's basically what we have. A bunch of numbers that do a bunch of things, and we can kind of see what each number is doing, but that doesn't mean we understand it. But if you can reverse engineer that, if you can reverse the compile, then you can understand what the software is. And I think that'll be a growing technology over time if people want to invest in it. It's very valuable. It'll teach us stuff we just simply couldn't have come up with ourselves. So yeah, we can learn the physics that they learn and see if it matches our intuition and maybe learn a few new rules. We often use models to understand processes by designing experiments with different forcing functions. How can AI models be used to design process studies? Yeah, so just as I was saying, if you learn the underlying physics, you can treat these models just like the models they emulate. You can force the original model, you can force the AI model, and they should do the same thing. If they don't, that means you're going outside of their training regime, and you need to identify when it doesn't know what it's talking about. It has like wildly varying output, and then you need to shore up that data so that it can run those process models. We often use models to understand. Yeah, we did that one. Not just meteorology, but also meteorology is looking to catch up to the ability of machine learning to accommodate emergent behavior. Traditional validation focuses on less agile PDE model components. So does catch-up in this activity involve better emergent validation than, say, CMC and ECMWF currently employ? I have to admit, I did not understand your question, so I'm going to reread it. traditional validation focuses on less agile PDE components. So does catch-up in this activity involve better emergent validation than ECMWF currently employ? So I'll focus on the last part. Do we require better emergent validation? I think we have certain confidence in PDE solvers that so long as they're stable, they're obeying the laws of physics within some degree. They can become numerically unstable, but we know their properties. We don't know what AI is doing because it's learned some completely new 10 million or 10 billion or 10 trillion lines of code software just from putting the data and turning the crank. So yes, we have to be much more careful with how we validate and test these models to ensure they're doing exactly what we want them to do. If there's more to that question, please feel free to repost. Am I missing any other ones bubbled up to the top? Currently, national meteorological centers develop and run weather prediction models, and there are a small number of prominent centers that both collaborate and compete to improve results. Is the approach of the future, as you see it, that there will be a small number of prominent centers run by for-profit corporations that will collaborate and compete on providing the best weather predictions? How will that be beneficial in the long run? So there will continue to be competition, whether the best models are national or private. Basically is up to them and how much money each of them wants to spend. ECMWF is staying ahead of the game by training their own AIFS model, and it seems to be very, very good. So they seem to be competitive in this space. Other places like, the weather company, Spire Weather, all these other places are also interested in training their own models. And they have a chance to be competitive because you can now learn very, very skillful models with less in-house expertise, without your own supercomputer. You just rent some GPUs once. So there's going to be more competition, I would say, or the potential for more competition. So if it's very valuable, there'll be more competition. Also, it's able to spread in lots of directions. We've just started with global medium range weather, but we're going to regional, we're going to AI downscaling. We can get all the way down to the building level eventually. There's a lot of potential for AI models to be built to fill in the gaps of things we couldn't do before and can do very quickly. So you're looking at real-time weather that could be instantaneous for your location, more accurate, more informative. It's a pretty bright future for numerical weather prediction. If you're not too worried about the disruption of jobs and stuff.
David,
So
there's one I think you missed that's higher up. So I'll just read it to you. It says, what is the skill of AI models on precipitation type? Performing well on temperature is one thing, but getting precipitation type and quantity is another.
Right. So when trained on Error 5, these models are not good at precipitation because Error 5 is not good at precipitation. They are just reflecting the data that you trained them. So basically, when you're giving a model a bunch of data, you're saying, this is what I want you to do. When you see this, predict that over and over and over again. And if you're giving it the wrong answers, then it's going to learn to do the wrong things. So to shore up those weaknesses, you need to give it more accurate prediction data or more accurate physical models that can predict precipitation. So you can do this by integrating multiple data sources into one model, like Error 5 and some other observations or other simulations, and have it predict the best results from each. Or you can create other models that post-process the original thing, which says, like, when Error 5 says this, what you really get is that. This is sort of like AI downscaling, but it's I don't even know what it's called. Is it just call it a post-processing model? But it can fill in plausible states based upon the conditional input from the Error 5 predictions. So there are a lot of ways to address this. If you get good data, you will get good predictions. And when we get directly to satellite observations of precipitation and ground station observations, and we get models that incorporate those directly, we're going to get much, much more accurate results in that. And it should predict all the different types of precipitation with the same accuracy you can measure them, or nearly. Any more that I'm missing? Should I drop to the bottom ones? Let's see. Do you envision that next-gen AI models will have the laws of physics built in so they cannot produce unphysical predictions? So there's something called Neural GCM out of a group in Google. I know these guys pretty well. And they come up with an interesting approach where they have a fully differentiable dynamical core that obeys the laws of physics as according to PDEs. And then they just use the closing terms, basically the physical forcings and such, They learn those from the observations and from the data. And their approach is an interesting hybrid one in that it's very, very accurate. They're able to get really great results. Unfortunately, it's still just as expensive as any PDE solver. So they don't get the performance boost, but they get an accuracy boost. So that's one way to generate better data for AI models. So you might consider a hybrid approach where someone builds neural, whatever these things are called, and uses that to produce really good quality data, which is then used much faster emulation. So it's not clear how this is all going to play out. Observations, hybrid models. What am I missing? How does the AI field consider the environmental impacts of massive computing needs? I kind of address that, which is that AI doesn't, people do. Are the energy skill comparison apples to apples? For example, GraphCast only has a few variables, including no preset. So is it truly cheaper than a GCM with hundreds of variables? That's a really good question. So yes, some of the savings comes from using partial information. And some of the savings comes from taking very large time steps. And some of the savings comes from more efficient compute on a GPU. Actually, quite a lot of it does. So it's hard to know how much is divided up amongst each of these like cost savings measures for a given model. If you want to generate all vertical levels of all variables, yes, it'll cost more, but you can kind of generate them on demand. So do you really need to know every vertical level across every variable all the time? Probably not. You need as many variables as are required to accurately predict the future weather. Then if you want to predict specific variables that are of use to you, you can use these post-processing models or rerun the prediction, because it only takes a second or two, to output other models. So you could like turn on and off math to say, these are the values I need right now. So you're still going to get a lot of savings on that level. The time step thing is pretty important. You're taking 1 6-hourly time step with one shot through the network. So the network is expensive-ish. I mean, not really. It's like an iteration, right? And you get a giant 6-hour time step. So you're just, however large a time step you're willing to take, you get a massive savings right there by not having to take every tiny little PDE solver time step in between. It can do basically the whole solve all at once. And the last thing was GPU acceleration. These things are natively trained and run on GPUs. And so you can do all kinds of ensemble members massively in parallel, and most of the operations are in parallel. The massive parallelization gives you a time speedup, if not a compute speedup. So yeah, yes and no. We still have time, like 5 minutes.
Yeah, about 5 minutes
Would
left.
you recommend a young meteorologist invest in NVIDIA? Now, invest, do you mean monetarily or by joining NVIDIA? The answer for now is yes, in both. How can AI deal with observation uncertainty? I already attempted and failed to answer that. How will the job market evolve for atmospheric science PhDs? How do we surf this wave properly at mid-career? This one's challenging. The whole economy, in my opinion, is going to change. AI is smart-ish now, and next year it's going to be a lot smarter. And by 2027, I mean, most OpenAI researchers estimate that AI will be as smart as any of us. We don't know if that's true, but if it is, why wouldn't they just hire an AI to do pretty much any remote job rather than you? And they will, because it's cheaper and the AIs won't complain, and they'll get better next year, and they're faster, and you can make 100 copies of them. So there's going to be a huge economic transition. This is outside of my realm of expertise, so I'm just speculating here. But when AI can do everything that we can do, how does anybody prepare? We need an entirely different kind of society with an entirely different kind of economics. The AIs can produce all the goods, grow all the food, do all the software, create all the entertainment if we want them to. But then we have to figure out how to get that to the people fairly, equitably. It's a new economic. So we need to be preparing for that, and nobody is. So we'll see what happens in the next few years. That should be exciting stuff. All right, let's see. Still a couple minutes. A bit of philosophy here. It's a bit scary when you hear we don't know what they do, but we might learn later. In meteorology, I don't see a danger of slippage. But when you think of other fields where AI is expanding and evolving, not knowing what AI is thinking and letting it evolve, we'll study it later, for me, is not very reassuring. Any comments? Merci. My French is terrible, by the way. Yeah, no, it's true. Given my choices, I would slow everything down. and very, very carefully step forward from here. Learning everything, letting Anthropic do all its work and people like them to figure out what the AI models are doing, so we understand them entirely and can reverse engineer them before we take the next step. This is not what's going to happen because there's such a massive monetary and military and social competitive advantage to having more advanced AIs. If you slow down, the other guys that you're competing with, we won't slow down. So everybody's racing forward to make the most powerful AIs as fast as possible. Basically, all you can do is cross your fingers and hope that it all works out, or wait for governments to regulate this very carefully so that we can proceed a bit more carefully. That's my opinion, purely my opinion, not anybody else's. Liquid neural networks could be advantageous. Is their initiative going in this way? I've only looked at liquid neural networks a little bit. They do look pretty interesting, much smaller things, more interpretable. There's not a lot going on within NVIDIA at that. It hasn't really piqued our interest. There's all kinds of methods to explore. But yeah, I believe there's potential there and probably great for an academic research project. Any that I missed?
I think, David, you got most of the ones on the list. I actually have a question for you as well.
Yeah.
So you talked a bit about AI and weather prediction, and then you also talked a bit about climate. What about seasonal prediction, kind of in between the two? What strides have been made using AI for predicting, next season, that kind of thing?
It's quite good. It's quite promising, actually. We've got internal projects on that. AI can learn seasonal to subseasonal stuff a lot easier than traditional models can because they have to take every little step and get every little step right. And then, over time they can drift. AI can take large steps and learn directly from observations and find all kinds of patterns that are not easily expressed in the laws of physics, like weird relationships. Maybe these relationships are like ad hoc, but if they can predict the future, then they're valuable. So I think there's going to be a lot of progress in that region soon. Seasonal first, because it's a little easier, subseasonal. But we have projects ongoing with that. I'm sure other people do. And I think, a couple of years out, we'll see some good stuff there.
Great. Well, I'd like to thank you very much, David, for a very inspirational, interesting, stimulating both presentation and then use of your voice to our advantage to answer all these questions that have come in. So the number of questions, I think, indicates the level of interest in this topic. And I really appreciate you making the time and despite your health issues, being able to provide this presentation and Q&A at the end. I will mention.
Thanks for the
thanks for the
invitation. Also, thanks everybody for all the questions. I really appreciate that.
We do have today is kind of an AI theme day, so we do have a number of contributed presentations and 3 oral sessions that proceed after this one. So those of you in the audience, you can look forward to additional talks on various AI related topics during the course of the day. So once again, thank you very much, David. Really appreciate the presentation. And I know it was very interesting and well received by the community as well. Thank you.
Thanks, everybody.